Hey everyone, hope you're doing well. Today is going to be a complete guide to factoring quadratics. Quadratics are a core part of high school math from probably grade 10 all the way up to grade 12. So you do really need to make sure that your factoring skills are at a good level, and especially how to deal with different kinds of quadratics, because depending on how they look in standard form, there are going to be different rules in terms of how we factor them. And that's exactly what we're going to cover. We are going to go over the rules for factoring simple trinomials, complex trinomials, differences of squares, perfect square trinomials, and then at the very end, we'll go over the FOIL method, which is how we expand out factored form. And that can be useful just to double check our work and make sure that we did everything correctly. And don't worry, I am going to break down the specific differences of all these different kinds of quadratics. But before we do that, let's think about why we even factor quadratics in the first place. So the key thing we're going to get with a factored quadratic is we're going to find its zeros. So let's imagine this is a quadratic in factored form, because that's usually what it's going to look like. We're going to have two bracketed terms. And if I set these bracketed terms to 0, and then I solve for an x value, that's actually going to be the zeros, or the x-intercepts of that quadratic. So in this example, if I take the first bracket, x minus 5, and I set that to 0, I can solve for x by just moving the 5 over here. So x equals 5 is one of my x-intercepts, and that just means that the point 5, 0 is part of the graph. And if I look at the second bracket of x plus 3, and I do the same thing, I find the second 0. Okay, so that gives us 2 points on the graph. Another thing it gives us is it can give us the x value of our vertex, because we know that the vertex of a quadratic is going to lie right between, in the middle of its x-intercepts. So if I find that midpoint value between the zeros, that will be the x value of my vertex. A simple way you can do that is you can just take your two x values, add them together, divide them by 2, and that should give you the appropriate value. So 5 plus minus 3 would just give me a 2. Therefore, our vertex in this scenario has an x value of 1. And this leads into the final reason why it's so important. This is giving us tons of useful information for graphing the quadratic in question. Let's go right ahead to the first kind of quadratic we can factor, and that is a simple trinomial. And a simple trinomial is just referring to the fact that our leading term, or the term that has the degree of 2, has a coefficient of 1. So usually when a term has a coefficient of 1, we don't write it in, but we can imagine that there's a 1 here. And when we look at a simple trinomial, sometimes it's useful to label our terms. So we would say this is our A term, our B term, and our C term. And for trinomials, we kind of want to solve a puzzle in order to factor it. We want to look at our B term and C term specifically, and we want to think of two numbers that when I multiply them, they give me my C term. In this case is a 10. And when I add those same two numbers, I get my B term, which is a 7. So whenever you have a simple trinomial, you can always set up this mini puzzle to factor it. And this one's not too bad. I can think of the numbers 5 and 2, because when I multiply 5 and 2, I get 10, and when I add them together, I get 7. So that's the puzzle solved. When we get these values, all we need to do is plug them in to the factored form, which is usually 2 bracketed terms with an x value at the very beginning. And we just need to plug in these values right after our x's. So here I have a positive 5, so this will be an x plus 5. Here I have a positive 2, so this will be an x plus 2. And that's all there is to it for a simple trinomial. Let's go over one more example just to really emphasize the rules. Once again, leading coefficient of 1. In this case, we want to multiply 2 numbers to give us a 6 and add 2 numbers to give us a negative 5. And this is a pretty common type of trinomial where our C term is positive, but our B term is negative. And in an example like this, the only way it's going to work is if we actually multiply 2 negative numbers together to cancel out the negatives. In this case, I can use -3 and -2 to get 6. And if I add those same values together, I get -5. So we're going to do the same thing we did with the first example. We're going to have x values to start in our brackets. But in this case, we're dealing with negative values. So we're going to have an x -3 and an x -2. All right, that is simple trinomials taken care of. Let's move on to complex trinomials. You can probably notice the difference. When we have a complex trinomial, we no longer have a coefficient of 1 on our leading term. We now have something greater than 1. And I just noticed that I don't like this C value here. Let's try a 15 there. And that should be a little bit easier to explain. All right. We're going to follow the same rules where we're trying to multiply 2 numbers to get to a value and add those same numbers to get to a different value. The difference is, instead of going straight to our C term for the value that we're trying to multiply to, I need to take the value of my C term and multiply it by the leading coefficient on my leading term. So instead of 2 numbers multiplying to give me 15, I am actually looking for 2 numbers that multiply to give me 30. Since if I take my C value, multiply it by my leading coefficient, that's the value I get. But luckily, we can still look at the usual value of our B term for the second part of the puzzle. Okay, multiplying 2 numbers to give me 30, adding them to give me 13, I should be looking for a 10 and a 3. Another difference with complex trinomials is we can't go right to the last step of plugging in these values into factored form. What we actually need to do is break down our B term into these 2 values that we just solved for. And I'll show you what I mean by that. I'm going to rewrite the entire quadratic, but I'm going to break down this 13x as one term being 10x and one term being 3x, and those values represent the numbers that we solved for in the puzzle. And then I'll just write in the rest of the quadratic. Now we're going to do something called factoring by grouping. I'm going to group together the first 2 terms and then group together the last 2 terms. And what I want to do now is I want to factor out the largest term that I can from each pair of terms. So looking at pair number 1, we have a 2x squared plus 10x, and the greatest thing I can factor out of that would be a 2x, and that leaves me with an x plus 5. Then, if I move on to my second pair of terms, I have a 3x plus 15. What I'm going to do here is pull out a 3, and then I am left with an x plus 5. And if you follow these steps correctly with a complex trinomial, you should get the same bracketed term on both sections of your answer. What we can do now to get to our final step, or to have it fully in factored form, is to put the terms that are outside of the brackets together in their own separate bracket, like so. I'm going to put 2x and 3 together, and then have our common term of x plus 5 as our second 0 in our answer. All right, I know that was a bit more complicated, but not to worry. We're going to go through one more example. And once again, I'm just going to change a value here just to make it a bit easier on myself. Let's go for a minus 18. Okay. Now here we could jump straight to the step where we're solving for the two values that we're looking for. But what I could actually do is right off the bat factor out a 3 from the entire quadratic. And that'll just make things a little bit easier in terms of the numbers that we're working with. Now I just need to look at these terms. So if I take the leading coefficient here of 2 and times it by my c value, I'm going to get a negative 12. So I'm multiplying two numbers to get me negative 12, and I'm adding two numbers to get my b value, which in this case is a negative 1. These ones are a bit trickier because our numbers are so different from each other. But if I take a negative 4 and I times it by 3, I get negative 12. And if I add 3 to negative 4, I end up with my b term. So this should work. I'm going to ignore the 3 until the very end because we're not really dealing with it. So let's just look at the 2x squared minus x minus 6. I need to break down my middle term into a minus 4x plus 3x. And then I'm just going to add the rest of the quadratic around it. Now we're going to group our first two together, or our first two terms, I should say, together, and our last two. In our first two terms, the most I can take out is a 2x, and that leaves me with an x minus 2. And in my second pair, I could pull out a 3, which again leaves me with an x minus 2. Once again, we have a common bracketed term, which means we're doing the right thing. So now I just need to put the 2x and the 3 together in their own bracket and write out the x minus 2. So this right here is our answer in factored form. Okay, this is going to be the bread and butter of quadratics, simple and complex trinomials. But we do have some special cases that can follow different rules. So let's take a look first at some differences of squares. What you're going to notice with these ones is we are lacking a b term. So we just have our squared term and a constant. And the reason they're called a difference of squares, difference is referring to the fact that we have a negative between them, and squares is referring to the fact that I can perfectly square root both of my terms, right? If I square root x squared, I get a value of x. If I square root a 9, ignoring the negative because you can't square root a negative value, you get a 3. So whenever I have two terms like this and they have perfect square roots, I can write out their answer in factored form, like so. I'm taking the value of their square roots and putting them together, and one of my bracketed terms has a plus between the values, and one of my bracketed terms has a minus between the values. And it's really that simple. You figure out what the square rooted value of your two original terms are, and then you put them together in one bracket with a positive, in another bracket with a negative. No problem. Let's try the next one, which is a bit more complicated, but it follows the same idea. We have two terms separated by a negative. I can square root this and get a 4x squared. And I can also square root 81 to give me a 9. So all I need to do is follow the same steps up here. I'm going to make one bracketed term with 4x squared plus 9, and then another with 4x squared minus 9. In this case, you can actually factor this a little bit further, because by creating our factored form, we've actually introduced another difference of squares right here. I could apply the same rules to the 4x squared minus 9 that I did to the 16x4 minus 81. And this is super common with questions like this, because you may notice this is no longer a quadratic. We have a term to a higher degree, in this case a degree of 4, so we're dealing with a quartic function. And this is a super common question on tests, because you're applying the same rules, but it might trip you up in terms of how it looks. So we can still apply the difference of squares rule, even when we're not dealing with the quadratic. And when we do this, it could be the case that we need to apply it twice, because one of our bracketed terms is itself a difference of squares. So let's do the same steps. 4x squared square rooted will be 2x. Square root of 9 is 3. So this can be broken down into 2x plus 3, 2x minus 3. And then we can't forget our original bracketed term here as well. We just didn't do anything with it. Okay, only one more to go. And honestly, it's not even its own type of trinomial in terms of having different rules to solve it. A perfect square trinomial is looking like a simple trinomial, right? We have our a, b, and c terms. However, if I take my b term, in this case it's a 6, I divide it by 2, and then I square root that value, I'm going to get my c value. So if I take 6 divided by 2, that's a 3. And then if I square 3, I get a 9. What does that mean? That means we can actually skip all of the steps of factoring a trinomial, and we can simply write our answer as x plus 3 squared. So when this is true, when I divide my b value by 2 and then square it, I get my c value. I can just add that value that I found of dividing the b value by 2 into my answer as x plus 3, and then just square the whole bracketed term. And this works for all of these kinds of trinomials. In the second example, I have x squared plus 10x plus 25. And let's test if it's a perfect square trinomial. I'm going to take my b value, divide it by 2, and square it. 10 divided by 2 is 5, to the power of 2 is 25. Therefore, it is a perfect square trinomial. And if I take my b value and divide it by 2, all I need to do is plug this into a bracketed term and square it. And that's my answer. So, lots to take in, lots of rules to remember, but we have a foolproof way of checking our answer in any case. No matter what, we can always check our work with the FOIL method. And FOIL is an acronym. It stands for first terms, outside terms, inside terms, and last terms. And by following this method, you can expand out your brackets to go from factored form back to standard form to check if you've done the factoring correctly. So these are some of the first examples that we worked through, and these were the answers that we got. We started here and we ended here. And if I follow the FOIL method on the brackets, I should go right back to where we started, thus proving that we did the factoring correctly. Let's look at the FOIL acronym. F is for first terms, and that refers to the first terms in both brackets. So the first term here is an x, the first term here is an x. If I multiply those two together, I get x squared. Now we're moving on to O, or outside terms, and I want to think of the very first term I can see, which is this x, again right here, and then the very last term, or the outside term, would be this 2 at the end of our answer. X plus 2 gives me a 2x. Now we're on to I, which is inside terms. So those are the terms right next to each other between the first bracket and the second bracket. So we're looking at the 5 and the x over here. 5 times x is 5x. And then finally, L is for last terms, which is the last term in each bracket. So here I've got a 5, here I've got a 2. Multiply those together, I get 10. And you can see that if I collect these two terms, I do get the quadratic in standard form, which is great to see. Let's just do one more for practice. This was our complex trinomial example. So our first terms are 2x and x. Multiplying them gives me 2x squared. Outside terms are 2x and 5, which will give me 10x. Inside terms are 3 and x, so 3x. And then finally 3 and 5 as our last terms, which gives us 15. Put these together, and we're right back where we started. All right, I think that covers all of it. This should be enough to deal with any kind of quadratic that you're looking at. Simple, complex, difference of squares, no matter what, you should be able to handle all those types of questions. Thanks very much for watching, and happy studying.